Dear students, in this class I will be talking about eigenvalue and eigenvectors. Okay. So mostly first we will be going for the definition of value of the eigenvalue and eigenvector, and after that finding this and relate eigenvalue to the singularity of a square matrix and use the power method for numerically find the largest eigenvalue and the magnitude. So this is the eigenvalue is so eigen means a characteristic, and which means west means value. So a characteristic value which actually signifies what the given system of function look like. Okay. So for example, a physical example is given over here. I can give you another example on this. So this is a Newton's formula. So these are relatively harder examples of it. So let me just give you a smaller and easier example in a matrix format. So like 4, 5, 6, 7. So what is the eigenvalue of it? So the 4 minus lambda, 5, 6, 7 minus lambda, and put this value equal to 0. Okay, so this is the easiest way. So now 4 minus lambda and 7 minus lambda into minus 30 equal to 0. Solving this system will give us eigenvalues. And here it's a quadratic, it will give you a quadratic. So in a 2 cross 2 system, EV equal to also 2. So you can see that. So parallel examples, but this is the easiest way to mark it. Now, general definition of eigenvalue and eigenvectors in square matrix. So first, n into n matrix not equal to 0, eigenvalue is like this. Okay. So how to find the eigenvalue of a square matrix? So exactly determinant value and equate with 0, as I said. So a, so 3 minus lambda, 15, this determinant equal to 0. Form a quadratic, solve the quadratic here. So Sridhar Acharya formula, here it is being solved. So minus b plus minus root over b square minus 4ac by 2a. Solve it in this way, you will get two values, and these are the two eigenvalues which we require. So the eigenvalue of this thing again, same 3 minus lambda, 1.50, and you can solve it and find the two values from the quadratic. This is also applicable for 3 cross 3, 4 cross 4, but this system is only applicable for a square matrix. Now it's a 3 cross 3. So remember that this is only happening in the principal diagonal. This is happening in the principal diagonal. Principal diagonal, the matrix is fixed from left to right, this one, not this one. Okay. And again, in that way, you just solve it, and at the end of the day, find the value. So with respect to every eigenvalue, there is an eigenvector. Just put these values over here, and you can find the corresponding vectors. Okay, this is the first vector, and the second vector and the third vector comes in this way. Now, there are some theorems which is useful now. Like theorem 1, if A is an n cross n triangular matrix, upper triangular matrix, upper triangular means like this, 0 is in the lower part, and values are like this. This is upper triangular, lower triangular exactly the opposite. And lambda is eigenvalue of matrix A if A is a if it's a singular matrix. A and AT have the same eigenvalues. Eigenvalues of a system matrix are real. Eigenvalues of a systematic matrix are orthogonal, and the last is determinant of A is the product of the absolute values of the eigenvalues of A. Okay, what are the eigenvalues of this thing? So the solution is this. So this is a triangular lower triangular matrix. It is. Okay, the eigenvalues of A are the diagonal elements of this. So if it is this, you don't need to solve anything, only write the diagonal values and your job is done. One of the eigenvalues is 0, is a invertible If lambda is a zero eigenvalue, then it implies that A is singular and non-invertible. So singular and non-invertible. If any one eigenvalue equal to zero, so the matrix becomes non-invertible. Given this eigenvalue in this kind of structure, just solve it. So what is the value of B if this thing is applicable? Okay, so B equal to A transpose. So A transpose we find, and same way we can do it with the normal eigenvalue calculation. So here the eigenvalues 3 are given. Calculate the magnitude and determinant of the matrix. So determinant equal to product of the eigenvalues. That's it. Okay. So find the eigenvalue and eigenvector numerically. We can do it like y1 ax10. So there are some questions here. This will be given as a homework at the end of this part. So find, using the power method, find the largest eigenvalue and the eigenvector. So this is x10 equal to 1. So 1, 1, 1 we multiplied with this. After we multiply, here we can see that we can get a 1 cross 1, 3 cross 1 structure. So it's a 3 cross 3, 3 cross 1. So you get a 3 cross 1. So once it has been done, lambda 1, lambda 2, and lambda 3, we will form another matrix. So the absolute relative approximation error is original actual value minus original value expected on divided by 2. So in that way, we can also find it out. So this table is not be required, and this is the end of the eigenvalue.